Mm. Uh, mm. Mm. Okay. Hi everybody. Yeah, hopefully you can hear me clearly. And of course, if I'm lagging, which might happen today, um, please let me know. I'll see how I can improve the internet connection here. Okay, let me first go to YouTube. Um, look at me. Oh, no. Okay. Okay, finally I can see the the chat on YouTube. Okay. Um, Page 157. Okay, we have a question on page 157. Maybe, yeah, before we begin, maybe I can take a look at the question itself. Okay. And of course, don't hesitate to ask your question in our group chat. Right, there are a lot of teachers in the group chat, and we are definitely willing to answer your question here. 157. Oh, it's this one. Now, for this question, I said it could be a challenge question. In the second on Tuesday on Tuesday. Right, this is actually a challenge question because if you have done all the previous questions, you'll see that we have more twos, less fives. But this one, you'll see that all of them are multiple of five. So actually, after you do the calculation, you'll see that we actually have more fives and less twos. That's why for this question, if you want to know how many zeros are there at the end of the product, you need to evaluate how many twos do we have after we do the prime factorization, right? So actually 5 to 2015, it can be written as 1 times 5 times 2 times 5 times all the way to 403 times 5, which is same as 5 to the power of 403 times 1 times 2 times all the way to 403. And you need to use the method that we learned before to find out, after we do the prime factorization, how many 2's are there? How many factors of 2's are there? Okay, so this is for this question. Now, this is just an explanation for the question on 157. Actually, we've done this one before, like 3 days ago. Okay, so you can go ahead and have a try if you still have question. Not really. We haven't finished all the topics in the book, and today we'll be talking about the last two modules, the counting and the combinatorics. Okay, so let me go back to the content page. Today we will be doing counting and combinatorics. Not only this one, we also have the topic 30, the inclusion, exclusion, also have the logical reasoning, the number puzzle. Right, so today the order will be a little bit strange. You might see, because I will start with the enumeration here, and the most basic way to do the counting, right? And go to counting 2D shapes, and then I'll jump to the last topic of our book, topic 30. Topic 30 will be the third one that we go through, and the last one will be the last topic of accounting will be topic 10. So this will be the order of the first half for the counting, and for the second half we'll do the logical reasoning. So the fifth one, the number puzzle, sixth one, and as well as the extreme values. Okay, so yes, hi. Hi everybody, this will be like the last day we have together on YouTube. This time. Okay, so let's just get started. Okay, so actually among the teachers, we have an agreement says there are two topics that that students will make a lot of mistakes. One of them is counting. The another one is the combinatorics, which you can say is most like logical reasoning sort of stuff. Okay, so you know why counting will be difficult? Counting is difficult because, well, for most of us, we just have no clue to count or in order. Right? It is very hard for us to be very, very careful and make sure that we don't miss out any, make sure that we don't double count some stuff. Right? This is very hard. All right. So counting is the type of question that even if that you probably know how to do, still you could get it wrong. Right. So this is this type of question. Now combinatorics is the type of question that I would say it's, if you know, you know. If you don't know, you don't know. All right, it's the type of question that is very hard to train. It's very hard to learn, to understand. There is no like a very typical trick to solve the combinatorics, the logical reasoning, right? It's more like an instinct. So today we'll be doing these two modules together in one day, in 2 hours. Okay, and let's start with the counting. Now, you know, I actually, the basic counting is easy. I think everybody, when you learn the maths, when you are super young, right, when you learn maths at maybe 2 or 3, the only thing that you can do is count your fingers, right? So this is actually the first thing that we start to learn about maths, counting. But you see, when you do the counting stuff, right, there is a word that is so important. And yet many of you will, not only you, many people will forgot about this, right? That is the order. Counting, the only important thing is that we're doing the things in order, right? So if you turn to this enumeration lesson, page 69, you'll see that, right, we have introduced a lot of different methods here, right, to do the enumeration, but actually all of them is about this one word, order. Do things in order. Okay, so uh and the method we're doing today will also be all about do things in order, not only in this topic but also next topic. All right, we'll do the things in order. Okay, so easy one easy way of one easy type of question that we have commonly seen is the page problems, right? The most common question says, well, for example, if you have 189 pages, then how many digits do you have, right? How many digits do you have? Or you can have, if you have 189 digits, then how many pages do you have, right? Pages, digits, as well as if we tear off one page of the book, then how many digits do we have left, right? So these are the common page problem. So you see, when you do this, right, the method you use is you start with type 1, that we think about the 1-digit numbers. Type 2, we think about the 2-digit numbers, right? And of course, 3-digit, 4-digit if you want, right? You can continue doing this. Now this is called doing things in order. Okay. All right. Now for the enumeration itself, not much things can be taught because it's just count. It's just you do everything in order. And in the book, you'll see another 2 different methods. First of all, is the number notation, right? So I'll start with a simple example. Right. So let's say your home is here. Now the ice cream shop is 2 blocks away from you, right? The ice cream shop is 2 blocks away. So how many shortest ways that you have to go from your home to the ice cream shop, right? And in most of the cases, you can only travel to the right, travel to the top. Now this is called the shortest way, right? So whenever you do this, you can use a method called the number notation. Right. So you look at the grid here, and there are a lot of points, right? So a lot of points. So the number notation states that you can label the number of ways to reach each of the point next to the point. All right. So for example, I start from the home. I only have one way to reach the home. All right. Now, if I want to go to this first red point, how many ways I have? I can only go directly from my home, travel to the right. All right. One way as well. Same for this one, one way as well. All right. So by doing this, eventually we can find out how many ways to reach the ice cream shop. And I'm sure everybody, like almost everybody, must have learned more or less about this method. Right. So this one is easy. 1, 1, 1. So 2, 3, 3, and 6. Okay, in total 6 ways. Right. And now the question itself can get a little bit more complicated with some specific conditions. All right. For example, if still from your home to the ice cream shop, right? However, this time you have to go through the middle point in order to get your money and then go to the ice cream shop. Then how many ways are there? Well, since you must go through this point, right? So we can first of all reach this point. There is still 2 points. So the first step is, if there is a point that you must go through, and you can divide the whole journey into 2 parts. First of all, from your home to the middle point, and then from the middle point to the ice cream shop. Right? So this is the first type of question that can make a little bit more complicated. And the second type is, let's say, for example, you have the roads here are having a construction, right? So that means you cannot pass through the middle point. Well, the idea is still the same. You can still go ahead and label your numbers, but the things you cannot pass through the middle point, right? So this time what you can do is, there's no way, 0 ways for you to reach the middle point. So let's just label as 0, and everything else is same as usual. All right, so in total, 2 ways to reach the ice cream shop. Right, so this is called a number notation. All right, and another way that you probably have learned before, which is a super powerful way, is called the tree diagram. Now, I like tree diagram because tree diagrams, they can help you do things in order. Right, they can help you do things in order. And with the tree diagram, you can solve a lot of questions that involves different steps. So your tree diagram can have step 1, right, a lot of trees. Step 2, a lot of branches, right? So whenever you have a lot of different steps, actually you can try to use the tree diagram to help you a little bit, right? So now, different questions have different method to use. Of course, there are more than these ways to do the listing, but for all of them, they are about this keyword order. Right? We're doing things in order. Okay, so let's just follow the idea we have here. So you see, these are the methods. You can go and read through this method and take a look at the example questions. Okay, so if we want to move from B to A, it can only move downwards or to the left, and it must pass through C. What is the total number of ways for B to reach A? All right, in that case, we can just do the number notation method, right? And notice that this is a must pass through point. So whenever you see must pass through, right, you can actually break down the diagram into 2 parts. First of all, B to C, this is the first step. And the second step, C to A. Yes. Oh, well, B to C times C to A is the answer, right? So actually you can just go ahead and label here. So you have so start from the point B. You have 1 way to reach point B, and these are all 1. Then 1 plus 1 equals to 2. 1 plus 2 equals to 3. All right. So there are 3 different ways for us to reach the point C. Okay, now let me change a different color, and we go from C to A. Right. So only 3 ways to come from C to this point. Same here, 3 ways. All right, and then 3, and then you continue. 3 plus 3, you got 9. Oh, sorry, 3 plus 3, you got 6. 6 plus 3, you got 9. 9 plus 3, 12. And 3 plus 6 now will be 9. 9 plus 9, 18. 18 times 12, 30. Okay, so with the number labeling method, you can directly find out, well, how many ways are there in total. But I see somebody says, well, B to C times C to A is the answer. Yes, that is correct. If we break down into 2 parts, you'll see that this one we have 3 ways. And if if you consider these two separately, completely separately, then you have 10 ways for this one. That's 3 times 10. Also works. Okay, also works. All right, so this is just the number labeling method. And you see, it's like this. It's like this. Okay. So this is about the number notation, and we can now. Well, of course, you'll see very similar questions at the back, and they are all similar, right? Actually, after you get proficient with the method itself, I think maybe you can solve all of these within 30 seconds. Okay. All right, same here. All right, some points that you cannot pass through. If you cannot pass through, then just label the 0 at the point that you cannot reach. Okay. All right. Part 2 is another one about counting, and it's another time that we need to use the order. Right? We enumerating in orders. How can we do this? So given a 2-digit positive integer AB, we define PAB, which is a new thing, right? It's the product of AB. So for example, P23, so it's 2 times 3, that'll be 6. P45, it will be 5 times 4, that'll be 20. Right. So I want to know how many 2-digit number are there such that AB is greater than PAB square. Okay, so how can we do the enumeration of this one? Well, we can actually enumerate based on the value of A. Right. So we can start with if A equal to 1. So if A equal to 1, then AB will just be 10B, right? 10 something B. So 10 something B, we can write it as 10 plus B, right? By the place value principle. Okay, by the place value principle. Okay, so we can start with A equals to 1, and then what are the possible values of B? So you see, if A equal to 1, then we have 10 plus B have to be greater than 1 times B to the power of square. Okay, so in this case, what are the possible value of B we can have? Think about it. Think about it. What are the possible value of B we can have? Right, actually, all you need to do is to just have a try, right? B can be, well, B can be 0, works. B can be 1, also works. B can be 2, also works. 3 also works. 4. Does 4 works? If B equals to 4, does it works? If B equals to 4, let's see what do we have. All right, 10 plus 4 and 1 times 4 to the power of square. Now this is 14, this is 16. Guys, does it still works? It doesn't. All right, so it's actually 0, 1, 2, 3, not 1, 2, 3, 4. Okay, 0, 1, 2, 3. So there are 4 different ways. Okay, so B got 4 different ways. If A equal to 1, all right, then how about if A equal to 2? So if A equal to 2, AB will just be 20B. All right, so it's same as 20 plus B. Okay, so the only thing that I'm changing over here is, well, I change it to 20 plus B is greater than 2 times B squared, which we can write it as 4B squared. Right. So once again, you can check by yourself how many values are there, how many possible values of B are there, and Actually, you can now see on the screen, right? There are 3 values of B, and always remember that we start with 0. Okay, if it's not specified, we just start with 0. While people are doing the calculation, a lot of you will forgot how to include the 0 in it. Right, but actually 0 is sometimes works. As long as it's not the first digit, 0 well works. Right. So actually just check one by one. I'm not using any like the special tricks. Okay, just check one by one. And yeah, I think you will get it. Okay, you will get it. Yes, 21 is the answer. Okay. All right, so I don't really like the enumeration because it's time consuming. But you see, doing things in order is very, very important. Even the solution here are still doing the things in order. We start with A equal to 1, A equal to 2, A equal to 3, right? Why times 7? Oh, we had a question, why here? Why here it times 7? Because starting from A equal to 3, right? The B can only be 0 and 1. 2 options in total. Starting from A equal to 3. Actually, for A equal to 3, 4, 5, 6, 7, 8, 9. All right. There's 7 values. For the 7 options, for these 7 values of A, each of them have 2 options, which is B equal to 0 and then B equal to 1. All right, so that's why we have 7, 2 times 7, and plus the 4 that we have here, plus the 3 we have here, in total 21. Okay. All right, so this is about enumeration, and for people, actually, this is the topic that I recommend even my P4 student to have a try. All right, because enumeration is like, as long as you know how to do things in order, this is like something that everybody can do. Oh yes, let's do the first rating of today. Okay, I will rate this as a 0.5, not based on the difficulty level, but actually based on how interesting is this. I will rate it as 0.5. This is like not interesting at all. All right, so it's just take a bunch of time, do the testing, all right, have a try, and it's really not interesting. Okay, I see a lot of it says 1 is 0.1, so let's just go with 1. Okay. All right. So for these questions, yes, please do the same. All right. There are a lot of enumerations that you have to done. And actually, all right, for the challenge question, it's also about enumeration. So don't forget that you also have a very powerful method that is called a tree diagram. All right. So actually, here's the hint for this question that you can use the tree diagram to solve. Hopefully, it helps a little bit. Okay, hopefully it helps a little bit. All right. So this will be our first topic. Now, just now I said we will move on to the counting 2D shapes, which is the topic 8, the earlier one. So we'll move on to the counting 2D shapes, the earlier one. Actually, counting 2D shapes, we again will start with the things that are very, very basic. Enumeration. Right, that's why I start with the topic 9, because enumeration is also a quite important method in counting the 2D shapes, right? I'm not sure how many of you have took the SASMO test before. I guess if you have took the SASMO test, let's type maybe yes or a 1 in the chat box and let me know. Right, so if in the SASMO test, while you were counting how many triangles are there, how many rectangles are there, right? I think the method that most of you used is what we start with. How many triangles was made up of one piece? How many triangles was made up of two pieces? Right, this was the method that we did. Now, which is called basically enumeration, but in order, right? In order. Oh, good job! If you get a gold, it's not that easy. Okay. Yes, it's just go ahead and count, but make sure that you do things in order, right? So this is the basic way of counting 2D shapes. Now, for 2D shapes, an, there are some other things that we need to know. All right. First of all, it's some specific method, or we can say it's the formula. All right. So let me give you guys some easy quizzes to do at the very beginning. Okay. So let's say I have this. Now let me erase one of them. How many line segments do we have here in total? Or I should say, how many different line segments do we have here in total? How many? One, two, five. Okay, not sure if you have learned the shooting method before. Right. So actually we have one, two, three, four, five. All right, and then move on. One, two, three, four. And then one, two, three. And then finally, one, two. And then in the end, last one. All right. So in total, actually, we have 5 plus 4 plus 3 plus 2 plus 1, which equals to 10 different line segments. Okay. So if you have forgot about this, you really need to learn it. All right. But for people that who indeed, sorry, 15, yes. I see my calculation is terrible. 15, sorry. All right. So, but for people who remember the method, right? Today I'll build based on the shooting method that we have learned. Some of you that have learned before, that we will learn what is the formula of this. Okay. So before we start, I'll introduce a new notation, which is called choose. So what is choose? So let's say if I have three candies, all right? Three candies. I want to eat two of them. Then how many ways do I have? There are three candies in total. I want to choose two of them, all right? And you'll see how to calculate it is just 3 divided by 1. Okay, so that's 3. Okay. Okay, actually 3 times 2 over 2 times 1. All right, so it's 3. Now, there are only 3 ways to choose 2 of them. Only 3 ways to choose 2 of them. Okay, so this notation C is called choose. Now, how to calculate the choose is like this. All right, so here I have 3 choose 2. That is simple. Now, what if I change it to 4 choose 2? So 4 choose 2, and this will be same as 4 times 3 times 2 times 1 over 2 times 1 over 2 times 1. Okay, so if you cross out one of the common 2 times 1s, this will be what you have left. And you will have like 6 different ways to do so. Okay. All right, so why am I talking about this? Is because actually we have a slightly faster way to calculate to count the number of line segments in this diagram, right? So you see, what do you need for a line segment? What you need for a line segment is just 2 ends, right? So choosing a line segment is actually same as choose 2 points as your two ends. All right. Choose 2 points as your two ends. And then how many ways are there to do? How many ways are there for us to do? Well, in total, we have 1, 2, 3, 4, 5, 6. 6 points, and we want to choose 2 of them. All right, so that will be 6, choose 2, and this is 6 times 5 over 2 times 1. So once again, you'll see that it's also 15. Okay, so if you're not familiar with this notation, choose, well, you might find yourself a little bit difficult to understand what we have here, right? Because you can see a lot of choose notation, okay? So I highly recommend you to study the choose notation first, the C first, before you actually do the counting 2D shapes. Okay. All right. So this is about choosing the line segments. Now, based on the line segments, actually, I can build up a lot of things. For example, right, I still have the same line segments with 2, 3, 4, 5, 6 different points. Right? I can, well, instead of talking about line segments, I can now change them into triangles. Right? Okay, now if I ask you how many triangles can you get here? It's actually same as how many line segments are there, right? Because I'm just building on the line segments that we just had it now. So choosing how many triangles are there in this question is same as, well, ask you how many different bases can they have, since they all have the common vertex, and we know that it's 15. Right? Yes, it's 15. All right, now talk after the triangles, we can also talk about the rectangles. Right. We can also talk about the rectangles. That, well, for example, if I have this, then how many different rectangles do we have? All right, how about this? You guys have a try first. Later, I'll show you the fast way to do. How many rectangles do we have here? I'm just drawing a simple diagram. I'll give you a small hint. 14. Not really. We have more than that. 26. We have more than that. 30. Actually, still more than 30. Okay, 35 is not close. So time to review the answer. Actually, all right, we can count like this. We know that, oh, very good, 36. 36 is the final answer. 36 is the answer. Okay. Why? How do we get 36? Well, neither you can count row by row, right? Every row you have 6, and then you can try to combine the rows together. How can we combine the rows together? 1, 2, 3, 4, 5, 6. All right, 6 ways to think of the rows. So that's why 6 times 6. Okay, but here's another way, and also it's called the formula. Now you think about it. How can we identify a rectangle? All we need to do is to find 2 vertical parallel lines, 2 horizontal parallel lines, right? So as long as we have determined which is the length and the breadth, we can determine the rectangle, right? So the question is, instead of asking how many rectangles are there, you can think about it like this. How many line segments can be our length, can be the length. So it's asking how many horizontal line segments are there? Now, based on what you just learned, there are 6 line segments, right? So that means there are 6 different ways to choose. Oh, of course, square is a rectangle, of course, right? So there are 6 different ways to choose the length. And the second question you can ask yourself is how many line segments can be our breadth? So in the horizontal direction, how many different line segments are there? We have, once again, 6. All right, so 6 different breadths, 6 different lengths. Combine them together, you got 6 times 6 equal to 36. Okay, so this is like the quick way for you. Yeah, this is like the quick way for you to find out how many squares are there. All right, so you see, here I give you a simpler one. Now I can make it a little bit more complicated by adding some extra lines. Okay. Okay, now let me add 2 extra lines. Let's once again do a short practice. How many different rectangles do we have here? You can now try to use the formula. Think about the 2 questions that I wrote here. How many different line segments, or I should say, the horizontal line segments can be the length, and how many vertical line segments can be the breadth? Let's see how many of you can get it correct this time. Only 9. Not really. Yes. All right. I see some of you already get the correct answer. So, first of all, 72, 75, 84. Right. So let's once again think about how many different line segments can be the length. So you can just only focus on the line segments we have here. All right. The horizontal line segments. Actually, we've done this one before. All right. We know that there are 15 different lengths are there. Only look at the the blue line. And now, how many vertical line segments can be our breadth? Still 6. Right. So that's why 6 times 15, you'll get 90. Okay. So the correct answer is actually 90. All right, so this is about the formula. Yes, I know that many of you might have not learned it before. It's kind of a new trick, right? But it's a very useful one. Very, very useful one. Okay, so this is why 6? Because if you look at how many different breadths you have, right? We have 1, 2, 1, 2, 3, and then change the color. 4, 5. Then let me change a different color. 6 in the end. Now it's just like ask you how many different line segments in this figure. That's how you count 6. If you have 3 parts, right? So that will be 6. Okay. Why is it 15? Why is it 15? It's here. Just now we have counted already. Right. So let me erase all the circles we have here. Now, if you look at the diagram, let me shrink it for you, make it smaller. All right. The blue line is same as the one that I've already drawn here. All right. So there are 15 different line segments for us as the breadth. Okay. Oh, sorry, as the length. And similarly, we have 6 different breadths. That's why 6 times 15. Okay. So the first thing is about well, about the formula, right? And the second thing that I have to add another page is let's come back to the idea of enumeration. Just now, I said one word about enumeration that is so important. Let's see, who here still remember is what is important when we do the enumeration? What is the important thing that we need when we do the enumeration? It's the order, very good. It's the order. Right. So this is like the key word we have. Right. So how can we now when we cut the 2D shapes, how can we make sure that we're doing things in order? Is you need to learn, all right, the basic ways to classify the figures. Right. So one way to classify the figures is based on their size. All right. So if I draw now let's say a 3 times 3 square grid, right? A 3 times 3 square grid. Okay, now I ask you, how many squares are there? Guys, how many squares are there? So this time you need how to do that. You need to know how to do that. Yeah, well, not really 9, not only 9, not only 9. 36. No, I'm asking squares this time. Yes, last time I asked about the rectangles, but this time I'm asking the squares. Right, so for squares, you can think about the size. Based on the size, how can we do the enumeration? All right, we can cut the 1 by 1. There are 9 of them. The 2 by 2. There are 4 of them, and the whole thing, the 3 times 3, there's 1. Right, so in total, yes, that will be 14. Actually, it's 14. Right, so you see, if I ask in a different way, even though using the same diagram, right, people make a lot of mistakes. Okay, so this is the first thing that we can classify our figure. Now the second thing, of course, when you do the SASMO test, you classify based on one piece, 2 pieces, 3 pieces. This is actually also about classifying based on the size of the figure, based on the size of the figure. Right. Okay. Now the second thing is based on the directions. Direction of the figure. Actually, it will be more straightforward if I show you this diagram. All right. So this one asks you, how many squares are there in the diagram on the right? Now, how can you classify this one? Squares. Well, squares does not equal to square. No, sorry. Squares does not equal to rectangles. They're not equal. Yeah. Yes, a square is a rectangle, but a rectangle is not necessarily a square. All right. So if you ask how many squares are there in the diagram on the right, all right, then you can classify based on the direction of the squares. Oh, slanted square, yes. All right. So you see here for the squares we have the one that looks like this, right? The normal one, and we also have some slanted squares. Right? So while you were doing the counting, that in this question you can try to think about 2 different ways. That you cut the upright squares first, and then you cut the slanted squares next, right? And actually, while you were counting the upright squares, right, you can also think about classify them based on the size. How many 1 times 1? How many 2 times 2? Now, do we have any 3 times 3? The slanted square looks weird. The size. What do you mean? Okay. All right. So keep this in your mind. I think that you can do the question by yourself. Okay. All right. So with the ways that we know how to classify and um count the things in order, right? I think it would be a good time for us to count how many squares are in the figure below now. Oh, my drawing is weird. I'm sorry. Okay. So for this one, right, I think that first of all the squares, they are upright. We don't have to think about the directions, but we can indeed think about the size of the squares, right? We can think about the size of the square. Now I'll call the smallest one a 1 times 1, right? And these ones, because it's made up of 4 squares, I'll call it 2 times 2. And for these, the big ones that you can see directly, I'll call it maybe a 4 times 4. Okay, so we can start with how many 1 times 1 square, that is the smallest pieces. How many smallest pieces we have here? The 1 times 1, that's this kind. How many are there? I think it's quite straightforward, right? There 8 of them. Okay, how about the 2 times 2 ones? Now the 2 times 2 will be a little bit tricky because you see the middle one is also 2 times 2, but if you think about this one, it is also 2 times 2. Right, so the 2 times 2, there are more than 8 of them. There are more than 8 of them. 10, okay. Yes. Actually, the 2 times 2, right? If you count carefully, there are 10 squares in total. So this one, here, and 5 in the middle, and the same for the other side, right? So there are 10. Okay. Now any 3 times 3. Any 3 times 3. Now guys, I remember I call this one a 4 times 4. Right. So any 3 times 3 we have. Seems like no to me, right? It seems like we don't have any kind of 3 times 3, but we can then jump directly to the biggest one we have. That is 4 times 4. How many 4 times 4 do we have? Oh, sorry. Accidentally show the answer. There are 3. Yes. Okay. Any larger ones? Any larger ones? I don't think so. Right? Because the maximum breadth is just 4. Okay. So that's why. Oh, here are the 3. In case that you didn't see all of them. Right. So I use 3 different color to show them. Yes. So here are the 3 4 times. Yes. 3. I used 3 different colors to show 3 of them. Right. So that's why we have 3 4 times 4s, and we don't have the larger ones. So let's just stop here. And hence, in total will be 8 plus 10 plus 3. That'll be 21. Okay? So as long as you do the classification correctly, it will not be that bad. Okay, so this is about actually enumeration again. I don't really like do enumeration, but sometimes it's like super helpful. And by doing things in order, you can make a lot of things simple, right? Yeah, so it'll be 21 in total. Okay. All right. So finally, I'll now introduce the last method that we need for the counting to these shapes, which is called, there are many different names for it. I call it adding line method. Right. So let me bring back to the question that we have done before, and let me ask you again. How many triangles do we have in this figure? Oh, we've done it before. Let's see how many of you can do this one this time. How many triangles do we have in this figure? Let me make this one larger. Oh, like what happened? Wait, guys, my WeChat site. I suddenly cannot see. Probably because. All right, guys, give me a second. Oh, that's why. Oh, 15. Yes, very good. 15. Okay. Now, what if I add a line to it? Now I add a line to it. All right, then how many triangles do we get this time? So what did I do to the triangle here? What did I do to the triangle here? I added a line, right? I added a line. And so after I add a line, I will get some new triangles, right? So actually, I already know that originally I have 15. All I need to do is to find out how many new triangles are there. And then I can know how many triangles do I have in total at this time. Right? So let's see how many new triangles are there. Now, before you actually try to find out how many new triangles are there, you first need to ask yourself this question. Why are we getting some new triangles? Why? Where does the new triangles come from? We get the new triangles because we have a line, right? We have an extra line. So what does this mean? This actually means all the new triangles will have this extra line as their sides, as one of the sides, right? So at this moment, all we need to do is to focus on this blue line and we count how many new triangles are created by the blue line, right? Yes. Okay. I already see says under the line, so we can, since the line have cut the triangle into two different parts, we can first of all take a look at this part. Okay. So guys, how many new triangles do we get here? How many new triangles do we get here? Here I get 32 in total. Answer 35. Right. Here I get 5. Right. Here I get 5. But now if I look at the top part, how many new triangles do I get here? So actually it's 15. Right. It's 15 again. Why? Because if you look at the top part, sorry. If you look at this part, all right, cover the bottom part with your hand. You'll see that the top part is once again something that we have already done, right? So this is 15. Okay, so that means I get 15 plus 5 equals to 20 new triangles, and together with the 15 triangles that I already have, so I have 35 triangles in total. Right, so this is called the adding line method. That if you get a complicated figure, for example, with a line in the middle, what you can do is you can take away the line first and then think about it, right? How many triangles are there without this line? And then bring the line back. See, right, how many new triangles do we get with this extra line, right? And then you can find out how many triangles are there in total. So, so the next example question, well, it will be just basically focus on this. All right. So actually, this is not a very typical question, but you see that we have a very, very detailed diagram for you, right? So you see, what we did is we get a complicated figure. Let's first of all make it simple. We remove the lines, right? The extra two lines that we had here. And then we add back the lines one by one and count how many new triangles were formed. Where's the extra line, right? So in the end, we can get our answer. Okay. So guys, because this question we have like very, very detailed solution. That's why I'm gonna do the next question together with you. Okay. We start with, since we get an extra line, this is the ugly line that we don't like. So we can start with, how about removing this line and think about how many triangles are there in this figure. Okay, so let's follow my step and we try to find out how many triangles are there in this figure. Now, the question gives you some hint because as you can see here, right, actually we can say, well, it has 3 different layers. Sorry, I'm so sick. Right, we have 3 different layers. Okay, so we can actually think about layer by layer. We start with, in each layer, how many triangles are there? Guys, in each of the layers, so let's just say focus on maybe the top layer. Right, how many triangles are there in the top layer? 10, very good. All right, each layer have 10. We have 3 layers, so 3 times 10 will be 30. But we are not really done because when you count the layers, right, you did not really count like this one, right? You did not really count like this one. So when we put in the layers together, actually there are some extra triangle being formed, right? This one and the red one, and also the similar 2 ones on another side that is not shown here. Right now, I didn't draw here. Okay, so when we put the layers together, we get another 4. So that's why in total, right, originally we have 34 triangles in total. Right. Okay, now it's time to add back the removed line. What did I say of the removed line? Why are we having some extra triangles? Because we added a line back and all the new triangles will have this line as a side, right? We'll have this line as the side. So all we need to do is to count, well, how many new triangles have been formed, right? And actually we can also do this thing like step by step, part by part. So maybe we can start with, well, this part. How many new triangles? How many new triangles do we form at this part? All right. Actually, if we think about it, yeah, three. Yes, very good. 3. All right. If we think about it, we count the new triangle is same as we count the points. All right. These 3 red points will form 3 new triangles with the given line. All right. So that's why there are 3 here. Now, how about this one? This one will also form a new triangle with the given line. All right. So this one also works. Okay, so actually counting how many extra triangle you can get, it's kind of similar as counting, well, each vertex will form how many new triangle with the extra line, right? So yeah, so here we now already have 3 and a 1, and we can check also this vertex. it does not really form a extra triangle. All right, maybe this vertex. So that is on top of it, on the top part. Right, on the top part, how many new triangles you get? Actually, this time you'll get a lot. All right. So so if you only look at this one, the part that I just shaded in this color, right? That will be another 3. All right, that will be another 3. Okay, but if you think about the yellow triangle that I just highlighted, all right, that will be another 6. Right, look at the yellow triangle. The yellow triangle together with our line looks like this. Right, so it will give you another 6. Right, so actually, all right, yes, very good, 6, 6. Okay, actually, in total, we will get a lot of extra triangles. 6, 3, 3, 3, and 1. Right, and I think that'll be all we have here. So we get an extra of 13 triangles together with the already existing 34. Right. Altogether, we can count how many triangles do we have in total. Okay. 34 together with the extra triangles we get. Okay. All right. So this would be next question over here, and actually this will also be the last question I go through in the counting 2D shapes. Okay, in the counting 2D shapes. So next topic will be about inclusion and exclusion, which is your last topic in the book. But you see, it's already 3, right? So I've decided that why don't we just maybe take a 4-minute break, guys? Let's take a short break, and we will be back at 3:04. I will be where we can talk about the inclusion and exclusion. A kind of a fun topic and not that terrible topic, right? But if you have learned it before, you'll know that we have something that's called the Venn diagram, where the basic one is like this. Oh, I forgot the rating of the last question. Oh, guys, yes, sure, you can do the rating for the last question. I forgot, where is it? You can do the rating for the last question. And of course, let's take a break. If you have any questions during a break, and the cut of the line, the removal of the line. 2, okay, 4, 3, 5. A lot of different ratings. 3, okay. Yeah, I think it's 3. I mean, it's not that easy to get it correct. Right, actually, even if it was me, if I do this question for the first time, I might get it wrong. So you see, this is about counting, right? This is exactly what I said about counting. That even though you know how to do the question, still you could get it wrong. You still could get it wrong, right? So you need to do things in order and make sure that you're following you're using the correct method of this one. Okay. Okay, I see the rating on YouTube and WeChat differs by a lot, like really a lot. What did you miss? Well, you missed a lot of things, basically everything about counting. No, it's okay. The playback will still be available, right? So maybe later you can check the playback. Um, but do check the playback. Actually, counting is very important. And today I'm like doing things in very details. Right. Um, so you can check later. A lot of formulas that we learned today. All right, it's 3:03 already, so I can slowly start on the inclusion and exclusion part. Right, so inclusion and exclusion is very closely related to this thing called the Venn diagram. Right, it is invented by this mathematician Venn, maybe a Dutch, I can't remember. Right, so Venn diagram is there are many different types of Venn diagram. We can start with drawing the Venn diagram, and actually drawing the Venn diagram is like one of the most important thing when we solve the inclusion and exclusion. Okay, so let me give you some examples. Um, well, so if I give you two groups of people who are studying today and the people who still have brain cells, right, then what will be the Venn diagram that looks like? It will be, it will looks like this one. Right. Right. Now you need to understand what does each part represent. Right. So this part is in the circle that represent people who are studying today. Right. But it's not within the circle for people who still have brain cells. So it will be like people who you guys on YouTube and WhatsApp saying have zero brain cells left. Right, so you will be in this part of the diagram. You will be this part of the diagram. Okay, now how about this part? This part will be people who still have the brain cells, but not studying today, right? Maybe people who are playing in the um, who people who are enjoying their March holidays. Okay, this is we're talking about topic 30, the last topic. Okay, and for 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 the middle part, it actually stands for okay. Oh yes, Rashid says still have the brain cells. Right, this will be stands for people with where is the brain cell, but at the same time also studying. All right, so you see, it's the overlapping part of the two circles. So this will be where's still have the brain cells and also study. All right, so you see, this is like a normal, a most common Venn diagram. Okay, now of course there are also other types of Venn diagrams. For example, all right, human. If I give you human and boys, now what would the Venn diagram not looks like? Right. So we know that all the boys are human, right? Hopefully. So so first of all, we can say, well, we have a very big group of human being, and um, within the big group, we have a slightly smaller one that stands for the boys. All right. So this is also possible type of Venn diagram that we could have. That is inclusive. One group is includes, contains another one. Right. We can also have another group maybe like the diagram for boys and girls. Okay. So if we draw the diagram for boys and girls, now it will be two separate circles, right? You will not have you will not have uh, any overlapping, any intersection of the two circles, right? So these are the basic type of Venn diagrams. Okay, so drawing the Venn diagram and understand which part represent which part represent which group of people is like very important. Okay, and actually there's another part on the diagram. Now I'll come back to the first diagram and show you again. I can draw a big box to represent everybody, to represent all the people here. All right. Now, who will be inside the box but outside the two circles? It will be the people who does not satisfy any of the conditions here. All right. So this will be people who are not studying and have no brain cells left. Right. So you see the Venn diagram actually are the most common ones. They do have 4 parts. Right. Part A is you only satisfy one condition. Part B is you satisfy another condition only, and part C in the middle is that you satisfy both conditions. And the part D outside is, well, if you don't satisfy any of the condition. Okay, I see some says make the boys bigger. All right, let's make the boys bigger. Okay, now it's a lot better. All right, so for the second diagram, you can consider this as like a donut shape. All right, a donut shape. Okay. Okay, so for the inclusion exclusion, when you have different groups of people that they might have overlappings, the key idea is well, you draw the diagram first, right? And like I said, you have to make it very, very clear that each region represents which group of people. Okay, bigger boys. I'm sorry, no more, not much bigger. Okay, that's already the biggest diagram for boys. So let's take a look at the example, right? And I like this example. I think teacher who made this took a lot of time to make this diagram, and it's so nice. It looks perfect, right? So in a particular school, primary 5 students sat for English and maths test, it turned out that 70% of the students passed English, 80% passed maths, while 10% failed both subjects. All right, so here's the diagram that we can have. So we have 2 circles. First one, the left one, for people who passed English. You can see 70% passed English. And for the circle on the right will be the 80% who passed maths, right? And we have, well, a region that is outside, does not inside the circle, that is for people who failed both subject, right? 10%. Okay, but then you might wonder, how did we get the 60% here? How did we get the 60% in the middle? Right, it's never mentioned in the question. So this is actually a backward use of the conclusion we have in inclusion and exclusion. Now, first of all, think about this. Right, so we have 2 circles. Now these are the inside the circle part, right? And you have 10% outside the circle. So in total, how many were inside the circle? In total, that would be 90% inside the circle, right? Right, it will be 90% inside the circle. But we know that 2 circles, they are 70% and 80% respectively. Then why, when we combine them together, it will be only 90%? Why would we only get 90% when we combine the 2 circles together? We combine the 2 circles together and it only get 90% because we have overlapping, right? And if you look at the overlapping part, it's been double counted, right? So we have to take away the double counting part. So this will be take away the part C, and then we know that this equal to 90%, right? Over 90%. Okay, so that's how we get part C equal to 60%. Okay. Okay, so this is like working backwards. Okay. Yes, very good. Minus 60%, right? So this will be what we have. Okay, so step 2 is basically explaining how we get the 60% inside here. And what we know is we know that there are 282 who passed both. So guys, 252 who passed both. People who pass both is which region, is which part of the diagram? Which part stands for the people who passed both? It will be the part C, right? So that is 60% of the total is 282, right? So now if you want to find out the total, whenever you are looking for total, you're looking for the unit 1, you can do 282 divided by 60, and you will be able to find out the answer. Okay, how to divide by 60? You can either turn this one into 0.6 or turn this one into 3 over 5. I highly recommend change the 60% into 3 over 5, since you will not get a calculator in the competition, right? So a fraction might be better for you. So change it into 3 over 5 divided by 3 over 5 is same as times 5 over 3. And you will get your final answer. That's 470. Huh? All right, of course, if you want to stick with like this way to do the calculation, definitely works. It definitely works. Just make sure, I don't really care which method you use to calculate the final answer. Just make sure that you don't make any of the calculation mistakes. Okay. All right, so guys, let's do the rating. It's the rating time. And after this question, we will come back to the counting multiple question, which I would say the example question is basically about inclusion and exclusion as well. All right, let's see. What is the rating for this question? 2 or 3? Okay. 1. 2 or 3 or 1. Okay, well, 1. Okay, I happy to see that a lot of users it could be 1. So you see, as long as you draw the diagram correctly, label the information on your diagram, right? This question should be okay for you. Should be okay for you. All right, so in the last chapter, we only have this one example question, right? But you see, for all the rest, for the practice questions over here, we don't have any of the diagram provided. So this time you need to draw the diagram by yourself, right? First read the question, understand the question. All right, find out what kind of diagram should we draw. Here, I've shown you 3 different types of diagram. All right, you need to find out which kind of diagram you should draw here. All right, so now we can come back to the counting multiple. So guys, please turn your book to page 79. So counting multiple, it sounds very hard, but it's actually a mixture of a lot of things that we have done in this week. The inclusion, exclusion, the factors and the multiples, a lot of things that we have done. We have done in this week. Okay, so and actually all you need to do is that we need to combine the things together. We need to combine what we have learned together. All right. Now, and a very typical type of question is, for example, this one. All right. If you want to use 1, 2, 3, 4, 5 to form a 3-digit number multiple of 5. right? How many such numbers that we can have, right? So here you need to use a bit of the number theory, but let's say, and as well as a bit of the multiplication principle. Yes, page 79. So guys, if we want to use 1, 2, 3, 4, 5 to form 3-digit multiple of 5, which digit should we start with? Which digit should we start with? There is a very specific condition for us. Multiple of 5. All right, so what do we know about multiples of 5? What do we know about multiples of 5s? We know quite a lot of things. 1, 2, 3, 4. We end with 5 and 0. Right? Now we only have the digits 1, 2, 3, 4, 5. So that means we have to put the 5 over here if we're looking for a multiple of 5. Right? And then we're left with distinct digits. So we're left with 1, 2, 3, 4 for the first 2 digits. Right? So we can just think about it. How many options do we have for this one? We have 4. How many options do we have for this one? We have 3 left. Right? So that'll be 3 times 4 times 3. Now don't forget here, I'm just showing that it must be 5. It only have one option. Right? So that's why 3 times 4 times 1 will be 12. Okay? All right. So counting multiple, one of the typical questions is like this. Right. You have to think about how to form the number, but always start with the special place, the special condition. All right, you see, what I ask you first when we do this one, what do we know of the multiple of 5? Because the last digit is the special place, the special condition we have, right? So always start with the special place. Okay, so the first question is actually about inclusion and exclusion, where here I help you draw the Venn diagram. Okay, now even though I think it was me who wrote this solution, is it? It's not really me. All right, but anyway, let's draw the Venn diagram here. Hopefully, it can help you better to understand this question. Okay, so it says it's neither a multiple of 8 or it's not a multiple of 4. Right, so here we actually have 2 conditions. Multiple of 8 and multiple of 4. Okay, so 2 different conditions, multiple of 8 and a multiple of 4. All right, so guys, now what I want you to do is to take out your pens or pencils, try to draw a Venn diagram for these 2 groups on your book. All right, what will the group that looks like for these 2 diagrams? Multiple of 8 and a multiple of 4. What will the groups looks like? Right, so actually these 2 groups, they are like very closely related. Right? How they're related? What do we know about the multiples of 8? Let's write down some example. 8, 16, 24, 32, right? So yes, very good. Circle in circle, you can call it a donut shape, right? So if you look at the multiples of 8, they are all multiples of 4. Yes, very good. And they are definitely all multiples of 2, right? So actually, if we draw on the diagram, it will be, well, first of all, a bigger circle for the multiple of 4 and smaller one for the multiple of 8. Right? So I have 2 circles, circle in circle. And which part of the diagram are we looking for? We are looking for that is neither a multiple of 8, right? So the first condition is a multiple of 8. Now would be everything inside the middle circle, or it's not a multiple of 4. Now, what kind of number on our diagram would be not multiple of 4? So every multiple of 4 is actually inside this red circle, right? So if we're talking about it's not a multiple of 4, then it will be the numbers that is outside, not inside the red circle, outside the red circle. Right. So actually I can draw another bigger box indicating all the 2019 numbers and the number we're looking for is neither inside the middle one or it's outside the bigger circle, right? And then I think it will be better for you to understand the solution over here, right? Because you see, what are we looking for? Divided by 9, we're looking for how many multiples of 8 are there, right? So the solution says there are 252 multiples of 8. That means inside the middle circle, there are 252 numbers. Okay. Now, we need to find out, yes, an even number that is not multiple of 4, right? So first of all, we're going to say the biggest rectangle will be all the even numbers. So how many even numbers do we have? We have 2019 divided by 2. That will be 1009, remainder 1, right? So we have 1009 even numbers in total. And we don't want the red circle. So we can take away the red circle. And how many red circles are there? 2019 divided by 4, right? So there are 504 red numbers inside the red circle. But now you see, we want to look for how many numbers are there outside the red circle. 109 minus what is inside the red circle. 505. Right? So that means the black part, the black shaded part, we have 505 numbers. And also inside the blue circle, we have 252 numbers. So based on the question, all we need to do, just add them together, and you'll get the final answer. Okay? All right, so that's why, like I said, draw out the diagram first before you actually do the question. Okay, you see how the diagram helps us over here. And that's why I want everybody to draw out the diagram over here. Okay. All right, so this will be the first example question. And yes, for the second example question, right? It's I mean it's kind of straightforward. So I'll leave the question over here for you. All right. So it's kind of related to the divisibility that we have done before. So it's once again a question that we probably have already done. Yes, I'll do the rating after I finish this. Right. Whenever you see a number, a composite number, right? Change into a product of the numbers. Now we know how to determine the divisibility. So here, 3 times 25. All right. We know the divisibility of 25. We know the divisibility of 3. So you can base on these two conditions and try to form the numbers. Okay. All right. So that will be for this topic, and that will be all we have today for the counting module. All right. So guys, yes, I know that you are waiting for it. So let's do the rating for this question. What is your rating for this question? 5. A lot of 5s. Okay, 2. Okay, I guess a 2. Okay. All right, 2, 3, 4. Yeah, let's just take a middle one. 3. Okay. Okay. Now this is not an easy question, but at the same time, it's not that bad if you can draw the diagram by yourself. All right. So finally, we can move on to our logical reasoning part. I know that you all like logical reasoning. It's like solving a crime scene, solving some interesting puzzles. Now, a logical reasoning, right? For the logical reasoning in NMOS, there are just mostly two methods that we can use. First of all, look for contradiction, right? But you know what? Before I talk about the contradiction, now I'm sure everybody knows what contradiction means, right? But can you actually determine which statement have contradict to each other? Let's say I give you an example. Right. So let's say, for example, I say that Mark says today is Monday. Wow, we are gonna start our NMOS live stream today. We're gonna start our NMOS live. So and Tiger says, well, today is Wednesday. It's my turn to do the live stream. Okay, now guys, are these two contradicting to each other? Are these two contradicting to each other? Now, if I say today is Monday, teacher Tiger say today is Wednesday. Now, are these two contradicting to each other? What do you think? No. Yes. Okay. Let's wait for more opinions. Yes or no? Okay. It seems like so far half. Okay. Half people says yes, half says no. A lot of people says yes. Okay. The correct answer is no, it's not. Why? What does contradicting means? Let me show you another example. Okay. Now, if I say today is Monday, but but let's say teacher Ethan says no, today is not Monday. Okay, now what can I say? Now clearly teacher Ethan is contradicting my statement, right? So in this case, we have one truth teller and one liar, right? Unfortunately, I'm the liar here, right? One truth teller and one lie, right? So whenever we have contradiction, it must be strongly disagree, okay? Directly disagree, right? So today is Monday. Now, if I say, well, you are not correct, you're not correct, then it will be contradiction, right? This is what we call contradiction. And whenever you see contradiction, you definitely have one truth and one lie, okay? But if we look at Teacher Mark and Teacher Tiger, well, we said today is Monday, today is Wednesday, but everybody knows today is Friday, right? Today is not Monday nor Wednesday. So what does that mean? Two of us are both lying, right? And this time we cannot say that we have a contradiction. We don't have a conflict. Right? We just have different opinions. Okay, so contradiction must be like strongly disagree, directly disagree. Okay, well, no, the opposite of contradiction is like in agreement. Right. So let's take another example. Let's say, Teacher Mark says, well, today, the counting is very funny. Counting is very interesting. Okay, very, very interesting. Okay, now Teacher Tiger comes and says, I agree with you. I totally agree with you. Right. So in this case, Teacher Tiger is like absolutely agree with me. Right. So this is called in agreement. Okay, this is called in agreement. And what do we know when two people have in agreement? Well, neither both are telling the truth. Right? The counting is indeed very interesting. Okay, both of us are telling the truth. Or both of us are telling a lie. Right? But well, counting is not interesting at all. It's so boring. Right? So whenever you have an agreement, well, you will have people who are both lying or people who are both telling the truth, right? So whenever you can find out contradiction or agreement, you can then use the number of truth tellers. You can use the number of truth tellers to find out who is actually telling the truth, who is not telling the truth. Okay. All right. Now this is called contradiction and agreement. Now the second method is the assumption method. Right. This is what like the detectives always use. Right. If this guy is right is the actual corporate, right? Now what will happen, right? And we find out, is there any contradictions? Okay, so basically what we do is whenever we cannot determine what is the true condition directly, we can assume that one of the condition is true and test the rest whether we have any contradictions, and then we can tell whether our assumption is correct or not. Okay. Okay, so let's just use this two method to do an example question. Of course, there are two tools that you can use when solving the logical reasoning. Right. So the first two is whenever you are doing the ordering, whenever you are trying to arrange the order, you can use a saying that is called either the magic arrow or the arrow, right? Where you can order who's the first, who's the second, can help you visualize this, right? And yes, you are learning to be the detectives, okay? So the second method is whenever you are doing matching, right? You have two different conditions that you want to match, right? Who did what, or who wears what color, right? Then you can use the table. Sorry, you can use the table method, right? Draw out a table, right? Let's say here we have A, B, C, and like some event number one, event number two, right? To see, or you can put tick, cross, right? To see whether this is which one match to which one. Okay, all right. So the tools are these two, or the magic arrow and the table. I remember in which case that you can use these two tools, and the method we're using is the contradiction or assumption. Right. So next question, the example question that we have here. All right. So you see 5 athletes participating in a 400-meter race. So whenever you have a race, right, then it will be, you have order, right? So you want to order things. So the method that you can do here, the tool that you can use here will be you draw a magic arrow. Because there are 5 athletes, you can have 5 different places. First, second, third, fourth, and fifth. Right? So whenever you are trying to ordering things, use the arrow. Okay. Now, here, each of them had made a statement, right? And we know that at most 2 athletes made incorrect statement. So you know what? I now want everybody to read through the 5 statements carefully and give me a pair. Give me a pair of contradicting statements. Contradictions. Okay, which 2 athletes they are contradicting to each other? Oh, I should move this one to the like to here. Should call better. Okay, 254 and 700. 254 and 700. Okay, so let's take a look at the statements that two of them made. 254 says, I was ranked second. 700 says, no, I was ranked second. Okay, do they have a contradiction? The answer is definitely yes. Right, they do have a contradiction. Okay, so whenever we have contradiction, what do we know? We know that one truth teller, one liar. All right, well, we can say one is correct, one is not correct. What else? What else? 53 and 78. 53 says, the champion has even athlete. Well, 78 says no. All right, so it's very direct contradiction. I was the farthest even, but I'm not the champion. All right, so these two, once again, they are contradicting. Okay, so we know one is correct, one is correct, one is incorrect. Now, but what the question also says, at most two of them are incorrect. Why? Now, who could be the incorrect ones? So it's within the two pairs, right? The two incorrect statements are within the two pairs. So what do we know about what the number 115 says? What do we know about what he said? He or she said? It must be a correct statement, right? Because you see, the incorrect statements are among this and this, right? And we only have at most two incorrect. That's why he must be correct, right? He must be correct. Okay, so athlete 115 says, this is correct. Let me tick here. The champion has an athlete number divisible by 5. So what do we know? If it's divisible by 5, that means the champion can be 115 or 700. Right, 115 or 700. Okay, problem is we don't know it's 115 or 700, right? So whenever we cannot decide, we have two options. Let's make an assumption. Okay, so it's assumption time. Now let's say if 115 is the champion, okay? So we start with assumption. If 115 is the champion, so I label at the first place. Now who ranked at the second? Let's first of all think about this. This guy is talking to number 115, right? But he says, athletes 115, you are not the champion because I was faster than you. So if 115 is the champion, so that means 254 is telling the truth, is telling the correct statement, or is telling the incorrect statement. If 115 is the champion, then 254 will be telling the incorrect statement, right? If 254 is telling the incorrect statement, that means 700 is telling the correct statement. So 700 will be the second. Okay, seems reasonable. But now let's take a look at the 53 and 78. All right, 53 says, well, the champion is an even athlete number. Because 115 is we assume 115 to be our champion, right? Then 53 will not be telling the truth. And 78 will somehow be telling the truth. 78 says, no, I'm the fastest among all athletes with even number, but I'm not the champion, guys. Does this work? Do we have a contradiction here? 78 says, 78 was the farthest among all athletes with even number. But look at our line. Right. Who is the farthest athlete with among all the even numbers? 700. Number 700 is the farthest. Where is among the even numbers, right? So that's why we found where we found a contradiction. So that means our assumption cannot be true, right? Our assumption cannot be true because we found a contradiction. That's why the champion will definitely be 700. All right, so let me draw a crown here. So 700 is the champion. Okay. Okay, so let's write it down. First guy is the 700, but since we know 700 is the champion, so let's check what 700 said. No, I was ranking in the second, but we know that he is the champion. So what does that mean? 700 is not making a correct statement, and 254 is making the correct statement. So who is the second one? 254, right? 254. And we're done because we're just looking for the first one and the second one. Okay. So yeah, but 700 is an even number. That's why just now, we can say that 78, we had a contradiction. But this time, since 700 is the farthest even number, he's the champion. 78 will be telling the lie. Well, this will be telling the truth. Okay. So the first one and the second one will be 700 and 254. So that's why the final answer, 700 plus 254, 954. Okay. All right. So you see, the solution here, it's very, very nice. All right. But while you are doing the question, I highly recommend you to take out the tools you have, the magic arrow while you were doing the ordering, the table while you were having the matching, while you were doing the matching. Okay. All right, so this will be for this question. Now, guys, let's do another round of rating, and then we will use our last 10 minutes to 15 minutes to go through our last topic, which is about the extreme values. 4. Okay. Yes, this question is like kind of complicated. Just kind of. 2. Okay. Rating 2. Sure. 2 or 3. 2.5. Okay, let's go for 2.5. All right. So the last topic is let me see. Last topic will be topic 10, I think. Oh, where is it? No, not topic 10. Topic 11. Okay. So last topic will be topic 11. So for the extreme value, right? There are some basic things that is must known. Okay. So for example, if I tell you a plus b equal to 12, I want to find out the biggest possible product of a times b. What will be the biggest possible product of a times b? If you have a try, you'll see that the best one we can have is 6 times 6. All right. So this is like the conclusion that you have to remember. Now, whenever you have a constant sum, the smaller their difference is, the larger their product. Okay. So you can highlight this sentence: smaller difference, larger the product. Yes. So this is the best we can do. Now, sometimes, even though I have no memory of NMOS testing, if they have a constant product, but it would be nice for you to have to memorize this. If they have a constant product, smaller the difference, smaller the sum. Okay, so it's not exactly the same. It's not exactly the same. Well, if you just join us, then unfortunately you have missed like 90% of the content today. And so actually, whenever we talk about extreme values, right, there are two cases. First of all, it's the most extreme case. All right. So, for example, if I want to share 300 apples among 5 students, right? So, and they all get different number of apples. So let's say A gets the most, B gets second, C, D, E. All right. So if A says, "Well, teacher, I want to eat more," how can I maximize the number of apples that A get? How can I maximize the number of apples A get? Right? Because in total I only have 300 apples, right? So the best way is, if I want to give A as many apples as possible, the best way is I give each one of them as little as possible, right? I give the rest of 4 only 0, 1, 2, 3 apples, and I give all the rest 294 apples to A. Right. So you see, in this case, I have maximized the number of apples that A can get. Right. Every get 60. Now, first of all, distinct. They all have distinct number. Right. So yes, we're going to make numbers less. Right. So this is called the extreme cases. Okay. This is called extreme cases. Of course, all right. Now, now what if I want the A says, "Well, teacher, I don't need too many apples," right? So how can I minimize? How can I minimize the number of apples each of them get? If I want to minimize the number of apples that A get, right? What I want to do is I want A to closer the number of apples A gets to be closer to the number of apples than other people get. Right. So ideally, it would be great if every one of them can get 60, 60, 60, 60. Ideally. No, he cannot get 0. That's the point. We specify that A will definitely get the most. Right. So ideally, the best way is, well, they all get 60. Right. So this is the idea, says we have the average case. Okay. So actually the extreme values, the extreme idea only comes together with these two cases. It's neither the most extreme or it's the most average. Right. So this is the idea of extreme values. Now, this is called the extreme principle. Right, with the constant sum, with the constant product. I'm going to try to remember this. And today I will try to go through. Now, this is like the question that I've said earlier, right? If we have a fixed sum, how can we maximize the value of the product? But you see, we have two numbers, right? We consider them as first number and the second number. If we want the product to be bigger, we make sure that they are as close as possible to each other, right? So ideally, it would be great if they can be 50 and 50. But since they are all whole numbers, right? So that means 3v have to be a multiple of 3. So the best thing we can do now will be 51 and 49. Oh, sorry, 49 cannot. The best thing we can do, 48 and 52. All right, so it would be great if they are close to each other. It would be great to very, very close to each other. So 2u equals to 2u equals to 52, 3v equal to 48. Now this is already the best way we can have. And find out the u and v, you can find out the final answer. Okay. And so I'm gonna skip this question. This is just like a direct application of the principle we have here. Constant sum, closer they are, bigger product. And for this example, right? I'll leave the work for you, but we'll do a simpler one. All right. So you can get yourself a scratch paper. So we'll start with, if you use 1, 2, 3, 4, we do a 2-digit times 2-digit. Okay. How can we make our product bigger? How can we make our product bigger? So we can first of all think about this question. All right. So 2-digit times 2-digit, we have two different places. We have the tens, we have the ones. All right. If we want our product to be bigger, then which one will be more important for us? The ones place or the tens place? The front, right? The front is the higher place value. So this will be more important, and hence we have to put like the bigger number at this place, right? So the bigger numbers have 3 and 4. So let's just put 3 and 4 here. Okay, second question, we're left with 1 and 2. Where should we put the 1? Where should we put the 2? Now, clearly, they will not give you the same result, right? They will not give you the same result. So actually, now you can think about what we have. Right. Based on the place value principle, the sum of these two-digit numbers will be 40 plus 30, which is the 10th digit we have, and plus 1 plus 2, that's the 1st digit we have. All right, so actually no matter where I put the 2, where I put the 1, right, it's neither 2, 1 or 1, 2. The sum of the two-digit numbers, it's fixed. All right, so we actually have a fixed sum. So what should we do whenever we have a fixed sum? We do fixed sum. If we see fixed sum, we want the two numbers to be as closer as possible. All right. So which one of these will be closer to each other? It will be 41 and 32. Actually, you do the calculation, you'll see that they are not the same. Okay? The product will not be the same. So instead of putting 2, 1, we were putting 1, 2, because 41 and 32 is the difference between them is only 9. But the 42 and 31, the difference between them is 11. And we know that if they have a fixed sum, smaller the difference give you larger product. Right. So that's why here answer should be 41 times 32. Okay. So for next question, it would be the same, but instead, you see, if we have here, the good thing is they're all two-digit numbers, so we can determine what to put at the tens, what to put at the ones first, right? But if they do not have the same number of digits, give it some zeros at the back to make them into the same digit. All right, so even though here we're multiplying a 4-digit times a 3-digit times a 2-digit, just give them some zeros at the back, turn them into all 4-digit numbers, and then do what we did earlier, try to find out the answer. Okay. All right, so guys, I think that will be all we have. That will be all we have for today's counting and combinatorics. All right, it's a quite packed lesson, a lot of content. So far, I think we have go through like most of them, even though some of the topics I skipped, right? But I think we have go through most of the topics in this book. All right, so hopefully this 5 days can help you a little bit for while you are preparing for NMOS. And yes, so let's end it here today with the old diagram I showed you yesterday as well. And don't forget that we will have a mock test this week. Okay, so if you got time, you wanna try how much you have learned in this in the 5 day live stream, you can go ahead and try out the mock test. Okay, so bye everybody. So for this time, yes, I'll just see you here. That will be all we have, and hopefully I can see you maybe next time when we do the stream. Okay. Okay. Bye bye guys. Bye bye. What if we don't meet? Yes. Um, you can always find me, and of course, another teacher in the group chat. If you have any question, yes. Thank you, guys. Bye bye. Bye bye. Hey, hopefully I'll see you guys next time. All right.